Since 1998, Formula One has been using frequency domain signal analysis methods to estimate their engine performance from measure sound intensity and applied the same technology to spy upon other teams by analyzing their footage. We knew that this technology had potential to be applied commercially to a UAV drone and be worthwhile for investors. By processing huge amounts of microphone data and training a machine learning model, it could be used to detect critical faults in automotive vehicles and warn the respective authority. Our objectives were to facilitate emergency services regarding vehicle breakdown and construct a noise map of UK. Therefore, the drone must have a high endurance with most operation relatively near to the ground. The reason for this is to accurately identify the signal with minimum background noise. Also, the drone should be low in cost to deploy several of them at the same time. We designed our aircraft focusing upon these requirements. We use analytical and experimental tools to identify components with little to no interference with sensors operation. Furthermore, we try to minimize battery capacity, reduce weight, and increase aspect ratio for maximum endurance.
We use Excel spreadsheets to break down the required mass and length of all the components of the aircraft to fit the requirements of our objectives. We have decided to go on with the V-tail because it has less weight and produces less induced drag. For the manufacturing part, we use this waterproof foam board material to create all the components of the aircraft as it is lighter and easy to cut. All the parts were attached by using the hot glue gun. We use rubber band to attach the wings and sticky tape for the tail. We cut holes for the servos using the box cutters and use wooden pieces drilled into the fuselage compartment. The servos is attached to the power pods that contains the battery and other essential payloads.
The payload consists of a Raspberry Pi attached to a matrix voice. The drone flies above street recording various sound sources and transmitting useful information back to the operator of the drone. The sensors are attached to the bottom of the drone to capture a less attenuated signal. Matrix voice is robust and powerful, measuring in at 3.14 inches in diameter. It offers a radial array of 7 MEM microphones connected to a Xylon FPGA with an integrated custom hardware accelerated machine learning technology. Matrix voice also include 18 RGB LED. Matrix voice is attached to the GPIO pin in Raspberry Pi and attached to the Pixhawk controller for power. Also, the Matrix voice uses an array of microphones with an inbuilt app to determine the direction and elevation of sound sources. Using the onboard computer, a spectrogram of the signal is created with the fast Fourier transform fed back into the machine learning model for classification.
So coming to the improvement section of our aircraft, if we have a chance of developing the other version, we could develop by modifying the design, adding of different materials to the structure, installing avionics of upgraded versions in latest versions, and modifying the whole thing, and addition of composites to the wings, which gives the structural rigidity and doesn't break while testing and doesn't get dismantle of wing and tail and lose structural integrity between those, and the whole final plane would result and look like this with the whole composites. And we could modify the code for optimization, for which results in better performance, and adding more efficient algorithm for sound classification, and adding noise filter to reduce background noise could be added, and whole the flight is ready to test and ready to fly.
Dronaria is a drone system that is highly capable of maximizing response time in an emergency situation in an urban setting. Using the machine learning algorithm, it could be used to classify sounds by identifying abnormalities in the signal. Due to its high maneuverability and top-of-the-line sensor, it can also produce a detailed noise map of an urban city.